Thanks for coming up, Chris.
Yeah.
It looks like the weather might be in our favor today.
It's great. This is why you live in Vermont, 68 degrees in August.
Absolutely. All right, here we are. Okay, well, I want to welcome everybody to Centennial Woods. My name's Walter Poleman. I'm an ecologist with the Rubenstein School of Environment and Natural Resources. And we're really just on the perimeter of the UVM campus at one of our 10 natural areas. And the natural area system at UVM is really a phenomenal teaching tool and also a research possibilities are endless with it as well, because for all the way from the shore of Lake Champlain to the ridgeline of Mount Mansfield, there are these areas that are set aside really to study natural systems and use them for education as well. But right here in Centennial Woods, this is probably one of our most visited, most beloved places. It's a little under 100 acres of forests and wetlands and trails. I'm really pleased that I'm here with my friend and colleague, Chris Brooks, who approaches things from an environmental policy and management and law perspective. And so together we're hoping to learn from each other about this place and share sort of an integrated understanding, or at least an integrated introduction to this place for you all today.
Yes. So in terms of the human impact on the land, there's an extensive land use history here in Centennial Woods. And the way that Centennial Woods looks today is a result of really dynamic change over time, both in terms of the natural processes that are shaping the land and shaping the wildlife habitat and the types of plants and animals that we find here, but also in terms of the social processes and the impacts that humans have had on this place. Starting thousands, tens of thousands of years ago, indigenous Abenaki were present in Centennial Woods. And over the past few hundred years, there have been a myriad of different types of land uses on this spot of land. And in exploring these woods, you can find clues to past land use history. So the impacts to this area are really what happens in an urbanized watershed. This is not removed necessarily from the urban area around it. It is a part of a whole. And so when you're down here, you're going to hear birds. You're also going to hear trucks and cars and planes from the nearby airport. 40 or 50 years ago, administration officials started to become concerned with degrading this wooded area, and there was a start to push for conservation here. And that ultimately ended up in the issuance of a conservation easement, which conserves this land in perpetuity for us, for UVM faculty and students to come in here and study the landscape, and for the entire community to come here to recreate, to get away, to walk on the trails. It's a tremendous resource to have.
You know, Chris, I just want to say that thanks for bringing up changing land use history. I remember the first time I came here in 1993, this was an apple orchard right here, and now it's developed pretty much right up to the edge. Though I'm sure the people who live right there use this all the time as well. So yeah, let's head down to the brook and check it out.
So it just rained this morning. Do you think the brook is going to be
It may be
a little bit silty?
Yeah, it may be. It's we didn't have a lot of rain here. We had a little bit, but it may. You know, it's a sensitive stream, that's for sure, with all the impervious surfaces around, so entirely possible.
So where Centennial Apartments are was an apple orchard?
It was.
Right,
yeah.
Okay.
Yeah, so that probably went in the late 90s.
When was the last time you were down here? Was this tree?
Okay, this is all pretty new. You know, we've had some pretty major storms. It could have been this major storm we had back in last October that really changed the meander of the stream. All right, let's head on down to the brook. Yeah. All right, only 5 minutes down the trail from the trailhead, we get to the raging torrent of Centennial Brook. Actually, not at all, as you can see. It's really a very modest looking stream, but it has had a tremendous impact on the shape of this landscape, really over the last 10,000 years since the glacier retreated. In fact, the power of water and its erosive power has really shaped the landscape. We've come down the hill from campus, and if, you know, as we look back to where we're going, you can go up another side of the hill, we're in a river valley. And if you're studying landforms and the superficial geology, really the stream has been down cutting through sand, which was this ancient delta of the Winooski River where it flowed into the Champlain Sea, you know, 12,000 years ago. It's down cut through that, so some of the soils a little bit higher up are really silts and then clays. There's a lot of clay in here that we've eroded down to. And then when we get down to the stream bed itself, you can see there's actually lots of rocks. Some of them are not that water-worked around it either. They're sort of, you know, in some ways freshly exposed glacial till, which sits right on top of the bedrock that underlies this area and the city of Burlington. So it's a fantastic laboratory for looking at geomorphic processes that the river, as it engages with the landform through time, and the overall topographic relief of Centennial Woods is really a microcosm of the larger Centennial Brook watershed. That combination of the landform and the hydrologic processes that everything is draining into. As this stream, as it's meandering along this bend right here, it's doing what streams do. It's depositing its sediment load on one side, this gravel, this kind of cut area, and then it's meandering again as well as it cuts into the bank on this side as well. So a great spot to look at river meandering. Centennial Brook actually has its beginnings, its headwaters at the high point of land in Burlington at University Heights, flows down through the interstate corridor, makes its way across Main Street, and then enters the natural area here on its pathway all the way down as it meanders through the woods here, ultimately emptying out into the Winooski River, where it's carrying not only its sediment load, but the water itself as it makes its way to Lake Champlain. Chris, what are your thoughts as an environmental policy person?
Sure. In terms of human impacts on the land and on this watershed, this is a great place to study what happens in an urbanized watershed. We're in the woods here, so the stream stability benefits to a certain extent from these vegetative buffers on either side. But if you pan out and you look at a topographical map of the broader area, you're going to see a lot of impervious surfaces, rooftops, parking lots, where when all of that rain in the surrounding area hits those impervious surfaces, instead of percolating through the soil down to the water table, it runs off somewhere. And it usually runs off directly into a culvert and enters this stream very quickly. So this is a stream that during a heavy rain event can rise really quickly. It's what we would call a flashy system. And so the morphology, the shape of this stream is dynamically changing in part rapidly because of all these impervious surfaces, and stormwater inputs into this stream are shaping the way that it looks today. And you can see that there are bridges down here, there are trails down here, other impacts of human activity that have to be adjusted because this stream is going to do what it wants to do as a result of all of the storm water that's flowing down here. And in the past, where the stream has eroded into the side of the trail, trails have had to be moved, bridges have had to be moved. There's also pollution down here. This is the most urbanized area of Vermont, and we will find E. coli and other forms of pollution in this stream, which you would expect to see in an urbanized area. Yeah, is there anything else you want to add to that?
No, I think that's good. Recognizing that humans not only are having to respond by moving trails, but they've put in all sorts of stormwater infrastructure to try to sort of mitigate the fact that there's so many impervious surfaces by creating ones that the water can percolate
So
through.
stormwater retention ponds, rain gardens, all sorts of green infrastructure has slowly been implemented over time, particularly on UVM's campus. And the whole point of that is just to slow water down and mimic natural processes and to prevent that water from rushing straight down to the stream and bringing sediment and pollutants with it.
Hey Chris, let's stop down here,
Yeah.
right at the edge of the forest where we can check out this wetland.
Yeah, so we're right at the edge of an upland forested area and a low-lying wetland complex that's bordering Centennial Brook. What this wetland does are the exact sort of processes that we're trying to mimic up on campus by slowing water down with green infrastructure. So this wetland here is a result in part because of beaver activity and damming and creating this wetland, but it serves so many important purposes for us and for wildlife. These are ecosystem services. So this wetland will serve to filter out sediment and other pollutants before they enter the brook. It'll serve to attenuate and slow down the stormwater that's coming down here. It'll attenuate a flooding event and allow that energy to be dissipated more slowly out over the floodplain and throughout the wetland, which protects downstream communities from flood damage. And it provides all sorts of really important wildlife habitat. So we've got a wetland here and then a steeper slope going up into the forest.
Yeah, and this ecotone here, this transition, it's pretty abrupt here. Suddenly we go from this wetland vegetation into the forest, just looking around, dominated by all these massive white pines and hemlock trees and beautiful dead snags where trees have died in place, providing habitat for all sorts of species. For instance, wood ducks, potentially could use spots like that if they're near a pond. So that connection to the wetland is important. There's many other, bird and wildlife species. Moose have been seen here in Centennial Woods and that use both wetlands and forested areas. Fisher and a whole diversity of bird species I'm hearing in here. And I'd love to explore this with all of you, this upland forest as it rises up out of the wetlands. Again, the changes in the hydraulic in the soil are really controlling this transition from wetland vegetation to upland forest in here. So I think it really, Chris, it really makes sense that we look at the soils in more detail here in a minute, because we really want to illustrate this idea of the landscape almost as a layer cake, where you go from the underlying geology that's been exposed by the erosive force of the streams, and we see the sediments that the soils are forming in here in the upland that date to processes that occurred 15,000 years ago as the glacier was retreating, and this whole area was at one time covered by at first glacial Lake Vermont, and then after that the Champlain Sea, and has slowly been exposed through time. And we can see down in the next layer, all the ferns that are down low, the deciduous trees that are coming up, the trees that are in the mid-story like this hemlock here, and then we get into the upper forested areas and all the way up towards the canopy, and we could really build a layer cake and think about the structure or the architecture of the forest, which is so critical to providing a diversity of nesting habitat for instance, all these birds that we're seeing. So great spot. Centennial Woods provides this diversity. All right, well, critical to the study of forested ecosystems is really kind of focusing on what lies beneath, essentially, because really we're looking at the vegetation that's occurring in a place, and there's a lot of factors that influence vegetation, including land use history, but much of it is tied up in the ecological potentials of the soils on a site. And so we wanted to take a few minutes here to dig into the soils of at least this spot in Centennial Woods, knowing that they're quite diverse across the landscape, but look here and see what we can learn about a few things about the the history of the site. And when I say the history, I'm talking largely about the glacial history and the post-glacial history. And we want to be thinking about the chemistry of the soil, how the soil particles interact with water. For instance, how dry or moist is this soil? And then ultimately, something about its nutrient content, and what do these plants here have to work with? How are they both influencing the chemistry of the soil, and how are they deriving their nutrition from the soil? So I've taken my shovel and I've dug sort of a 1 foot by 1 foot square and pulled out the sod here, which has its own integrity. And actually you can see there's layers in the soils that show as you go down from the surface. And what I'd like to do is have you kind of focus right here on the soil profile. It really is interesting. A lot of people don't pay a lot of attention to what's happening beneath, but when you actually take time to dig in, you can see that there are colors as you go down, and this vertical profile occurs, and that really exposes what soil scientists call the soil horizons. We're going to get to that in just a minute, but before we do that, I want to talk a little bit about what I had to take out of the soil pit to expose the horizons, and that is the soil particles themselves. And boy, just feeling this, it is a very soft, light soil. There are no rocks in here. Unlike down in the stream where we saw a lot of rocks, this is very uniform, very fine particles. In fact, as I feel these, you can figure out the texture of the soil or the particle sizes by feeling them. And largely, this is some very, very fine sands and silts in here. Two questions arise from that, and one of them is, how did these particles get here to begin with? And then also, what happens when rainfall interacts with this soil? Does it kind of get all contained to the surface, or does it percolate quickly down through the soil? In answer to the first question, and we kind of referred to this earlier, where did this come from? Well, these fine silty particles, absence of rocks means that this is really a post-glacial environment in which there was a body of water once covering this area, and fine particles percolated down and collected. And basically, I think it's safe to say geologists have figured out that this is an ancient delta of the Champlain Sea, the saltwater body of water that basically filled the Champlain Valley as the glacier retreated northwards and the waters of glacial Lake Vermont receded, and the salt water of the Atlantic Ocean kind of filled in this area that was compressed by the weight of the glacier. So we basically have water deposited sediments that were an ancient delta, and as you go down deeper and deeper into this area, you get into really silty particles. And so that's what the soil is forming in, fine sands and silts. And as you may know, that if it's really sandy and you basically poured a glass of water, it would percolate down quickly through here. As you get into finer and finer particles like really silts and clays, the water cannot percolate as quickly, and we tend to get more poorly drained soils. But it's safe to say that these soils are they're pretty well drained. And some of that is when we look at the soil horizons, we see lots of kind of rusty colors in here, which means that oxygen has gotten in there and almost rusted the soil and oxidized the iron. So that's a little bit about the texture of the soil and the origin of what we call the parent material of the soil. Let's return now to those horizons, and it's really cool to look at this. This top horizon here, this upper part, is actually the contribution of the forest environment itself to it. It's the needles and leaves and twigs. You know, there could be owl droppings in here, decomposing animals even, but this top section here is really what we call the O horizon, and it's the organic material. And I'm going to take some of this and put it in my muffin tray here to kind of separate it out, and we can see these horizons as we go along. And below that, you can see there's this darkish horizon here, and if I pull some out, it's this beautiful dark material, and this is because it's the combination of organic material mixing with mineral material, and this is called the A horizon. And together, these are really the topsoil. So we have the O horizon, which stands for organic. A is just the first letter of the alphabet. But that's that typical zone where organic and inorganic materials combined. What's really interesting on this bed, and you might be able to see it here, is there's a slight little bit of ashen color right below the A horizon. And this often occurs in acidic environments right at the base. And I'm going to put a little bit of that in here, and you can almost see the color difference as you go from the dark to sort of a lighter color. In some environments, this horizon is really well developed, and we call it the E horizon. And it's the horizon of maximum leaching that is occurring as organic acids and water move down through and basically deposit minerals and humus down into the horizons below that. And as we get down into that, we get down to what is called the B horizon. And you can see here the B horizon has a dramatically different color. It's this really rusty color here. And it turns out that as water moves through, and actually, you know what I'm going to do is put this up here in this here. Let me put it up in this well. And you can see that the water would be flowing from here to here to here to here. It's stripping irons and depositing them down here. And then it turns out that as the iron is oxidized, because these soils are pretty well drained, we get this rusty colored B horizon. So we've gone to O to a little bit of an E forming here, into the B horizon. And as we go down further, this may go down for several inches. It often gets lighter as you go down because it has less of the iron that's been deposited. And if I had my auger with me, I might go down even further and get down to really the original parent material of the soil, which is not really interacting with roots and the organic pieces, and we get down to that silt that is really originally deposited in the Champlain Sea. So these are the horizons again, and this is a really a great feature to illustrate here in Centennial Woods. Really important, though, to the plants is to look at the chemistry of the soil. And so what I want to do is, I brought my pH kit with me that has some it's got some reagents here. It's got a chart that basically shows us, can allow us to detect the pH of the soil. And as you probably remember, pH is a measure of the, essentially the acidity of the soil. And if we get a little more technical than that, it's really the concentration of hydrogen ions in the solution of the soil that we're detecting. And pH is a logarithmic scale. It goes from 0 to 14, at least theoretically, with 7 being neutral in the middle. Most soils go from a pH of about 4, maybe to 8.5 in Vermont, with the average usually around 4.5 or 5. Most are like that. Here in the Champlain Valley, things are a bit different because of all the clays and the proximity to the carbonate rocks that lie beneath. But we're going to do a pH test right here, and we're going to test and see what the pH of the soil is here, because it turns out that by measuring pH, you can infer what the available nutrients are to plants as well. Essential nutrients like calcium, potassium, and magnesium. Really, a low number like 4 means you have a really acidic soil with a high concentration of hydrogen ions, and therefore a lower concentration of other positively charged ions like calcium, potassium, and magnesium. If you have a higher number, like 7 or close to 8, that means that you have a sort of a more neutral soil, lower concentration of hydrogen ions, and more available plant nutrients, like calcium, for instance. And so what we're going to do is we're going to test that right now. So I'm going to take one of my reagents, reagent N, which basically reacts with hydrogen ions. So I've put 2 drops in that well. I'm going to go down about 10 centimeters, and I'm going to add just enough of the soil particles there to soak up that reagent N. Then I'm going to mix it together. And what's happening now is that the reagent is interacting and reacting with the hydrogen ions that are in the soil. Now I'm going to make that, it's already, there's a color change occurring, and I'm really making a flat sloping surface there. Then what I'm going to do is take this reagent M. All sounds sort of mysterious. This one doesn't really react, it just really makes the color come out so that we can compare it to our color chart. So I'm putting some on the surface, and then I'm supposed to wait up to 2 minutes to get the full change. But you can already see here that now I'm getting a color change, and if I align it there, I can figure out, well, what color is that turning? And actually, this is fairly acidic soil here. It's not turning blue, it's actually staying sort of yellowish green. And I would say, just looking at this, is that we have a pH of about 4.5 here, which is on the acidic side of things. And when you think about that, what would contribute to that? Well, the fact that we have all these pine needles and cones and really all this acidic material that's leaching down into the soils really influences the pH. And the fact that we don't have rocks here with calcium carbonate, we have all this kind of sands and silts, these don't do a whole lot to buffer the acidity. And so we're getting fairly acid soils. And that is very much reflected in the vegetation around this site. Pine trees, white pine can grow very well in acidic, well-drained soils. Hemlock, which also is very common in the site, does particularly well in acidic soils too. And we're missing a lot in here the species that are rich site indicators. So when we look at the forest here, it's largely a reflection of what lies beneath. Life is impacting the soil, but it's also being affected by it.
So we've hiked up here a little further from uphill from where Walt dug his soil pit. And we're at an interesting point in the woods where downhill from here you can see the younger forest, dominated by white pine and paper birch. And uphill we've got a more mature forest. There's a very old white oak tree here. And one of the things that I want to highlight is this space is an anthropomorphic space. There are examples of human impacts to the land everywhere you look if you search it out in Centennial Woods. Here's one example, which is just an anomaly, but this dates back to university activity with the ROTC bunker. There's a large cement wall here. Before the university owned all this land, however, there was agricultural pursuits going on here. And you can find evidence from that as well. Right here, attached to this old white oak, is some barbed wire, which dates back to dairy operations that took place on this land in the late 19th and early 20th century before it all got bought up and consolidated by the university. As I'm standing here, I can hear trucks on the interstate. I can hear planes from the airport going overhead. There's all sorts of interesting examples of human hands and impacts on the land here. So when you're walking through Centennial Woods, you should be thinking of this not as a place that is separate from the urbanized world around. It's not an escape to some pristine natural area. It's actually a connected whole. There's human activities going on here continually through history, and this parcel of conserved land is directly connected to all of the urban areas around it.